Okay, so a couple of videos earlier we had discussed about the spherical coordinate frame, and we showed how the spherical coordinate frame is defined, how one calculates the velocity of a point that is represented by a spherical coordinate and acceleration and so on. In this video we will take an example where we apply these ideas of spherical coordinate frame. So the example goes as follows. So this is an example of a rotating gyroscope. You could consider it to be a spinning top as well. So here is the XYZ coordinate frame, the fixed XYZ coordinate frame, and assume that there is a gyroscope which is basically a rod, and at the end point of the rod there is a disc, and the disc rotates about this, spins about this rod. Now the rod makes an angle theta, a constant angle theta, and let's say that this point is O and this point is O prime. Then if you project O prime onto the XY horizontal surface, then that projection, let's call that point Q, makes an angle phi with the positive x-axis. Now we are going to use a spherical coordinate frame and also furthermore, let us say that this phi dot is a constant. So phi dot is constant and theta is also constant. The length of the rod from O to O prime is capital R, and the radius of the disc is small r, and at this point on the circumference of the disc there is a point P. Alright, and the disc is turning at a constant angular speed. So let me just make sure that I have the diagrams properly done. So this is spinning, the disc P is spinning about this rod with a constant angular velocity omega. So I'm going to indicate that in the diagram, and our goal is to find the velocity of the point P. Okay, so first what we'll do is we will sketch, so in order to show the spherical coordinate frame that we are going to use in solving this problem, we are going to sketch a sphere. So let me just okay, so here is a sphere. This is a hypothetical sphere. The sphere is being drawn only to illustrate the spherical coordinate frame. The sphere is of radius capital R. So clearly this point O prime is on the circumference of the sphere because the distance from O to O prime is capital R. to denote the position of this point O prime, we use the spherical coordinate frame. And if you recall, the way to conceive of a spherical coordinate frame is to consider one way to understand it is to basically consider latitudes and longitude at the point of interest. So I'm going to draw let me just redraw this latitude. Okay, so this latitude is the latitude which contains this point O prime, and if you recall, we also need to draw the meridian or the longitude which contains this point O prime. So I'm going to draw the meridian as well. Okay, so here is the meridian which contains the point O prime as well. Okay, so let me just make sure that I have good focus here. Alright, so here this dashed line is the meridian, and here this dashed line, which is a horizontal circle, is the latitude, and the sphere is of radius capital R. So using this latitude, meridian or the longitude, and the radial line from O to O prime, we have the unit vectors. We have ER. If you recall, E theta is along the meridian pointing from north to south, so, and that is E theta, and E phi is along the latitude going in the counterclockwise direction if you look from the top. So that's E phi. Now with respect to this E phi, now keep in mind that E phi is always going to be horizontal because the latitude is always going to form a horizontal plane, and E phi is tangential to the latitude. Then at a given instant, the point P is making an angle alpha. So let me just write it more clearly. I shouldn't probably use the black ink for better contrast. So it is making an angle alpha, and the spinning rate alpha dot is equal to capital omega, which is also a constant. Okay, so what I mean by this is that it is a constant. Okay. All right. So with this as our setup, we are ready to solve this problem. Let us just mention that find the velocity of P. Okay. All right. So the way we are going to proceed is that we are going to start by saying that Vp is equal to Vo prime. O prime is the center of the disk, plus omega cross rho plus rho dot r. And if you recall, omega is the net angular velocity of rotating frame rho is the vector which is going to go from O prime to P, and rho dot r corresponds to the velocity of P relative to O prime within, and I underline within, the rotating frame. So as observed within the rotating frame, what would be the velocity of P with respect to O prime? Okay, so these are the main components. Our goal is to find Vp. So find the velocity of P, we are calling it Vp. Right. So now let us consider so our rotating coordinate frame is r theta phi. So let us also make sure that we put down what is the sequence of these vectors that form a right-handed coordinate system. So it is, the sequence is er, e theta, e phi. And what we mean by that is that er cross e theta gives us e phi, and so on. And you can also check that by noting that if I curl my finger of my right hand from er towards e theta, then my thumb of my right hand is going to be pointing in the direction of e phi. Similarly, if I curl my fingers of my right hand from e theta to e phi, then my thumb is going to point in the direction of er. So that's the right-handed coordinate system definition, and we need to write this down up front so that we know how to carry out these cross products. Now first we need to find the velocity of O prime. Okay, so first we note that r O prime is nothing but capital R ER, right? And so therefore V O prime is equal to r dot ER plus r ER dot. But r dot is 0 because we have a gyroscope or a top which has this length to be a constant. So what we have is r ER dot. Now what is ER dot? We know that the time derivative of a unit vector is nothing but, of a rotating unit vector, is nothing but omega cross ER, where omega is the net angular velocity of the rotating frame, right? So what is the angular velocity of this rotating frame? So we note that phi dot is in the z direction, phi dot is directed in the z direction, and theta dot is directed in the phi direction. Okay, so basically our angular velocity omega is equal to phi dot Ez plus theta dot E phi. But Ez is not good because Ez is not one of the unit vectors. We need to express Ez in terms of ER, E theta and E phi. But that is easy to do because you see the z direction, if you take the cosine of that, it's going to, the z direction, if you take a cosine of that, is going to align with the ER. And if you take the z direction and take the sine of it, it's going to align with the negative E theta. So therefore we have phi dot cosine theta ER minus phi dot sine theta E theta plus theta dot E phi. So that's our angular velocity omega. Okay. Right, so we have the angular velocity. Next, what we do is we need to calculate this ER dot. So therefore ER dot is equal to omega cross ER is equal to, so I need to do omega cross ER. So ER cross ER is 0, of course. E theta cross ER, if you see, E theta cross ER is going to go in the opposite direction, so we'll have negative E phi. So then when we take this cross product, we have phi dot sine theta this is going to be E theta cross ER. So E theta cross ER is negative E phi. So, okay, so we have that. And then we have E phi cross ER. So E phi cross ER is going to give us E theta. So we'll have plus theta dot E theta. Okay, so then we can say that therefore, so going back to our VO prime, we have VO prime is equal to R times phi dot sine theta E phi plus R times theta dot E theta. Now note that in this problem we have mentioned that theta is a constant, which means that as the gyroscope is spinning and precessing, note that this phi dot, this motion leads to what is called a precession of the gyroscope. So as the gyroscope is spinning about its axis, the axis itself is spinning about the z-axis. So that spin of the axis is called the precession, and the gyroscope is maintaining a constant angle theta. So that is basically a precession with a constant nutation angle. So this angle theta is often referred to as the nutation angle in gyroscopes, and so in this case we have a precession under constant nutation angle. And so since theta is not changing, we go back to our VO prime and we set this second term to 0. So therefore VO prime is simply R phi dot sine theta E phi. Alright, so we have our first vector. We also, by the way, have our angular velocity vector. If we go back to the original velocity equation, we need this angular velocity vector, and we have it. So we have the expression for the angular velocity vector. Okay. Now, so let's call this angular velocity vector equation 1. Let's call this equation 2, and let's call this equation, the original velocity equation, as equation 0. Okay, so the next thing that we need in equation, so this is equation 0, this is equation 1, the angular velocity vector, and VO prime is equation 2. So the next thing that we need in equation 0 is rho. So let's formulate the vector rho. Now, the vector rho is, as we have mentioned, it is the vector from O prime to P, right? And it is quite easy to formulate it. First of all, it has a length of r, because that's the length of the disk. So if you do r times cosine alpha, it is going to project that O prime onto the E phi direction. And if you then do r, small r, sine alpha, as you can see, it is going to project it on the E theta, but in the negative E theta direction. So negative r sine alpha E theta. Alright, now we need to find so let's call this equation 3. And then finally we need to find the relative velocity of p with respect to O prime in the rotating frame. And in some cases it is rather easy to see that velocity and formulate it intuitively. In other cases you may have to do some algebra to find this out. And we have shown this that to find the relative velocity within the rotating frame, what you do is you take this row vector and differentiate it with the consideration that these rotating vectors are considered momentarily not rotating. So when you find this derivative, this is a special derivative where we do not differentiate these rotating vectors. What that does is it gives us the velocity of p with respect to O prime within that rotating frame. Okay, so for the moment you forget that the frame is rotating and you take the derivative. So if you did that, then what you would get is r negative r sine alpha. Alpha dot, keep in mind, is this capital omega. So negative r sine alpha omega e phi. This is typically in the Greek letters, this is capital omega in the Greek letters. I'll just refer to this as omega as we solve this problem. And then the second term is going to be minus r cosine alpha omega e theta. And note that I am not differentiating e phi and e theta, although in the absolute sense they are moving, so their differentiations must be taken, but that differentiation is being considered as part of this whole operation that is being done in equation 0. Okay, so that's our equation 4. So now all we have to do is we have to assemble these terms here. So first let us do the computation or the calculation of omega cross rho. Let's get the expression for omega. So omega is phi dot cosine theta er minus phi dot sine theta e theta plus theta dot e phi. Okay, and then we do a cross product with rho, and that is r cosine alpha e phi minus r sine alpha e theta. Now before we proceed, we make the observation and thereby make the simplification of theta dot equals 0. The nutation angle is not changing, and hence we don't need to carry out these cross products when with theta dot, because it's a 0 term. So continuing with this cross product, then er cross e phi, let's keep the cross product convention here. So er cross e phi is negative e theta, so we will have minus r cosine alpha phi dot cosine theta e theta, because we are doing r cross phi, which gives us negative e theta. Then we do r cross theta. R cross theta gives phi, so we will have minus r sine alpha phi dot cos theta r cross theta, so that's e phi. Then we have theta cross phi, so theta cross phi gives er, so we have negative phi dot sine theta r cosine alpha er, and we don't need to do the theta cross theta because that's 0. So this is our expression for omega cross rho. We can call this equation 5. So now it's just a matter of making substitutions. So we say substituting 5, 4, that'll take care of 5 and 4 will take care of this guy and this guy, and we just need a VO prime, so that is equation 2 into equation 0. We have VP is equal to VO, so let me just substitute the expression for VO, that's R phi dot sine theta E phi, capital R phi dot sine theta E phi. Then let us substitute the expression for omega cross rho, so we have minus R cosine alpha phi dot, and this is small r, keep in mind, cosine theta E theta minus small r sine alpha phi dot cosine theta E phi minus just going to keep the same format, r cosine alpha phi dot sine theta ER, so that's this term. So we have copied down omega cross rho, and then we are left with the terms from equation 4, so minus r omega sine alpha, this is small r E phi, minus r omega cosine alpha E theta. Alright, so now in the last step what we'll do is we will combine the terms that have E theta, combine the terms that are in the E phi direction, and then combine the terms that are in the ER direction. So in the ER direction you see that what we have is minus R phi dot cosine alpha sine theta, and there is no other component in the ER direction. In the E theta direction you have minus, so you have this term and that term, small r phi dot cosine alpha cosine theta plus small r capital omega cosine alpha E theta let me just check one thing here. Okay, I think we are good. And then we have we group together the terms that are that form the component in the E phi direction. So we have r phi dot sine theta, should put a plus here, minus small r phi dot sine alpha cosine theta minus small r omega sine alpha E phi. Okay, so that then is the expression for VP, And that is basically it for this problem. So the goal was to just derive the velocity for the point P, and we have used the rotating spherical coordinate frame, and the rotating frame is such that it is attached to this axis. Okay, so the frame is attached to this axis and is moving with the axis. Now, independent of the frame, the disk is spinning. So the spin of the disk is independent of the rotation of this rotating frame. So keep that in mind. We have a rotating frame here, which is actually not fixed to the disk. It is fixed to this axis. Okay, so the rotating frame is fixed to this bar, and the disk is rotating independently of it. Yeah, seems to be fine. I'm just making sure that I have written the expressions correctly. Okay, so that is it for this video. This was a brief problem, but to illustrate the application of this spherical coordinate frame. Just to keep things in perspective, this was the setup of the problem. It was a problem consisting of a gyroscope that spins with a constant angular velocity and which precesses with a constant speed of phi dot. So this phi dot is called the precession speed, and it is considered constant. Furthermore, this gyroscope makes a constant nutation angle theta with respect to the vertical, and under these considerations our goal was to find out the velocity of an arbitrary point P on the circumference of the disk, and given that the disk itself is spinning about the rotating axis with a constant angular speed. Our rotating frame was a spherical rotating frame, or a spherical coordinate frame. It was attached to the bar that connects the disk to the origin, and the disk was rotating in addition or on top of the rotating frame. So that's the description and solution of the velocity of the point P. So thank you so much.